When we go out into the field, you can configure the lander any way that you want. So this was done in conjunction with JPL. So thanks to Serena for hooking us up with them. So this is a low cost way to get to Mars. So this is a hard impact lander. So we use that design in their arms. So you'll see this big drag skirt arms. And then we put a lander design on top of that. And so that's what I'm going to show you. So this is what it looks like. This is what we're going to see in the field. And so these arms here, and this is JPL's design, this is not ours. This is the umbrella. So this is how the lander actually enters the atmosphere, crash lands, crumbles the nose of it. And then the drag skirt is going to be pulled away. And we're left with an instrument package that's in the center of that. So what we're going to do tomorrow is go out and see a full scale version of this. And click next. So this is all the different instruments that you can play with. And I know we cannot ever put this many instruments on Mars. I also probably wouldn't want to because it would just be a big disturbance to the flow. But what we can do is we can take each different group's design or individual's design, and we've designed this so that you can actually easily, place anemometry at different heights, both sonic and cups. We also have articulating arms, so it's not actually going to just stay in the body. If you want it to stay in the body, you can, but you can articulate the mast arms out. It rotates 360 degrees. Can you click next? I think I'll just try this. So what we have to work with, and so tonight over beers or whatever you're going to be doing, try to get your design ready. So we're going to have a vertical array of cup anemometers, and that's going to give us mean flow. So that's going to be no turbulence fluctuations, but we can do a time average to get law of the wall. We can extrapolate down to see what the roughness elements would be. We can pull that out, that articulating arm goes out so it gets away from the lander body. We also have a vertical array of sonic anemometers. And so this is where we move from just looking at mean flow and we can get the turbulent fluctuations. So one of the things I brought up earlier is what's our sampling volume? What's our sampling frequency? And anytime we're calculating or doing Reynolds stress decomposition, we have to choose an averaging window. So what period would that actually be? What window would that be? And that actually should change with height, depending on your turbulent spectra. We also have a couple of GoPros. So I've heard today a lot about, let's do photogrammetry or structure for motion. So we can do that here. We have a LiDAR, and so this is how we can get estimates of surface roughness or topographic change. So we can use that, pull that into our models, and then try to resolve the shear velocity on the surface. So just some mechanical design considerations. As I said, it can rotate 360 degrees so that we can point into the wind, and it has a compass on it so that we can actually know our orientation. Each arm not only moves articulates out, but it also articulates horizontally. You can also remove arms as well. So for example, this is all the instruments on it, but we're pretty much going to take that cup anemometer mast off pretty quickly because we're not going to have cup anemometers on Mars because of the density difference. So we can take that off. We can put on a 200 hertz sonic. We can compare that sonic sampling frequency to the typical RM Youngs, which are sampling at about 32 hertz. And we can see the differences in what we're actually missing in the turbulent spectra as we move with height. And we have the horizontal positioning as well. So what's your idea? Do you want to just use one sonic, two sonics, three sonics, four sonics, five sonics? What sampling frequency? There's all kinds of design considerations. So tomorrow in the field, you'll be able to test yours out. And then I'll come back on Thursday and I'll show you the results. So that's tomorrow.
Great. Thank you so much. We're going to switch over to the next presentation, which is Alejandro Soto. Thank you.
Okay. The sharing now. Okay. So this is just a quick little advertisement of an instrument that I've been developing. I call it Hura. Hura is the root word in the Taino language for wind. It's where we get the word hurricane from. And this is a laser anemometer, velocimeter, and particle characterization instrument. Technically, it does anemometry, nephelometry, and tomography. So what we're doing is we're measuring particles of dust in the air as they move around. Since they're moving with the air, we get the wind from that. We get a particle count. And because of some things we're doing with lasers, we're also getting the size, but not a single effective size. We're actually getting a 3-axis size. So we get the shape of the particles as well. Just quickly, because this is a lightning talk, fundamentally what we're doing is we have 3 lasers, red, green, and blue. They can actually be infrared as well, but it's safer to use colors that you can see so you can keep yourself safe. They coincide in the center, which is the observing volume, is where the laser beams overlap. Each laser beam has a fringe pattern imposed on it. We use what we call a quasi-chirp mask to get that fringe pattern. In this example, this cartoon I have here, the fringe pattern is even in all directions. It's actually, we've now designed it so that it has the width of the bright and dark regions varies in one of the directions so that we can actually back out the direction of the velocity that we measure. But the idea is that as the particle passes through that center, it forward scatters light that is detected by photodetectors. And you see a little arrow in this picture here on the left saying photodetector assembly. In this design, there's 5 photodetectors opposite from this each one of the lasers. You can only see one set right now really well from this angle. But the photodetectors are measuring the forward scattered light, and each set of photodetectors has filters just to see one of those sets of lights. And then by measuring just in one photodetector and looking at the spacing of the fringe pattern and the light detected. So we have these fringe patterns in the laser beams, light that as a particle passes through the laser beam, the light scattered off the particle encodes that fringe pattern. However, the spacing of the fringe pattern changes as a function of the speed of the particle. And so we can back out the speed of the particle with just the laser fringe pattern, scattered light, and one photodetector. We have multiple photodetectors because then we can also, we're basically measuring at different points in Fourier space the signal and looking at that signal, the different parts of the power in the Fourier spectrum. We can actually, in the upper right of this slide, you can see a simulation of taking a simulated particle, measuring it with the laser light in Fourier space. We're basically measuring different scattering angles, and we can back out the reconstructed particle using tomographic techniques. So this is a prototype I've been building with internal money from Suri. And so we can see on the bottom right, there's a picture of a tabletop version of this instrument. It's based on the CAD drawing on the upper left, but you can see the actual thing with hardware. And then in the far bottom right is a picture of it on a rover. This is the Sandy rover from one of Ryan Ewing's projects, where he took a rover out of Iceland to do a whole bunch of other work unrelated to that, but I got to tag along, stick my instrument on there. So I have a bunch of Iceland data that I'm going to try to process and go through demonstrating the value of this instrument to measure dust. And I didn't mention this. It's designed primarily to get dust in the range of like 1 micron out to 100, 150 microns. You can design it for different ranges. The technique slates changes a little bit when you get to larger particles. So if you wanted to go after sand. But basically the idea is I wanted a way of simultaneously measuring wind, dust, concentration, and the velocity distribution associated with that dust concentration. With the time I have, I think that's it. Thank you.
Thank you very much. All right, so our last demonstration today is going to be Jack Gillis. It's right there, so if it could just be on him.
To the light. So tomorrow we'll have this set up in the field with everything attached to it. But this is the sand tree, which stands for Sand Transport Instrument. And the principle of operation is these black things on the side are optical gate sensors. So there's a beam between the one side and the other. And as particles go through, they interact with the beam. So then we interrogate that. Oh, sorry. We interrogate that information at kilohertz speed. And there's an onboard microprocessor, which then allows you to get an estimate on, you can actually see like the leading edge and trailing edge of particles. So you can get an idea of how fast they're traveling and their size. And once you know the size and the speed and the number, moving from top to bottom, you can integrate over the height of the saltation cloud and come up with a mass flux. So it's currently designed, this is called the Santry 2, which has no directional, it has limited directional capability. And we've been using these in the field already, the Salton Sea, to, you've got about a 60-degree window to look at particles that are approaching it in the saltation cloud. And it's extremely useful if you know you're only going to get transport from a very limited direction, or you could use more than one if you've got a bi-directional kind of setup. We also have a different, the Santry 1 is actually a standalone multi-direction, omnidirectional. That's a bit harder to design because basically when you want to log the data has to be telemetered wirelessly. So you would be like Bluetoothing over your data to the data logger. But we've had very good success. They've been very robust. I think the next sort of design phase is to go from a chunky silver rectangle to maybe something that's more aerodynamic and where the optical gate sensors are actually away from the bluff body effect of the unit itself. But we've compared them to Big Spring number 8 physical samplers. We're getting very good relationship between our flux measurements done with our algorithm and the actual mass flux as measured in the BS&E. So hopefully we might get some sand transport tomorrow, but otherwise we'll have the whole thing set up at the dunes and we can throw sand at it even to get a response. And yeah, thanks for your time.
Okay, it looks like we have 10 minutes for questions. So the first question is from Derek Jackson, who asked, are there issues with background particles being in the way between sensor pickup point and observation volume point? This is for Alejandro.
Yeah, so that can be an issue. And what we've done is two things. We've designed the field of view of the photodetectors to not see the entire line of the laser. And the second thing is any particle passing through one of the lasers, but not the central point, will only generate a signal in one of the laser channels, not in all three. So we can also, in the data analysis, separate out any signals that we got that only show up in one channel versus all three.
Thank you. Another question from Banfield is, how do you disambiguate speed from size on the Santry?
I'm not sure I have a good answer for that. Basically, I think what you see is as particles translate across the beam, you can see when the particle enters, and then as it exits, the smaller the particle, the less it covers the beam. And then from that, you can sort of get the speed of that particle across that known distance. Now, a large particle would essentially completely block the beam for a time. And again, we have issues also with like glancing blows, I guess. You could get the edge of a particle transversing the beam. Hope that helps.
Yeah, this is a follow-on question or clarification. So you're doing essentially particle counts, right? And so you have to assume a particle mass to be able to compare it to the BSNE. But you know, where we're doing similar field work, we actually have different compositions. It's bimodal, and so particles. If it's quartz, it's one mass. If it's cinder, it's going to be a different mass.
It's a density issue. For the size, you'd have to, if you are going to eventually get to a mass flux, you would have to know the particle size distribution and the density so that you could say, this is how much that would represent on a balance. So that's probably the toughest part of coming up with a really robust algorithm. And what we're doing now is sort of, what it's doing now is it's able, we're saying it knows what the particles are around 80 microns that have gone through each of those.
Okay, we have time for one more question. Anyone in the room? Okay. Oh. All right, and last question from Steve Metzger. In order to fully realize the high resolution benefits of SandTree 2, do you plan to incorporate wind speed sensors, and can you get them to sense the same volume being studied for particles?
We cannot interrogate the speed of the wind inside the optical or through the optical gauge sensor. What we're doing now is having just a nearby anemometric measurement of wind speed or a profile of wind speed, and then right beside it we have the it's no different than having, you know, an array of BSNEs with height, only instead of collecting the particles, you're counting them and running them through an algorithm to give you the estimated mass flux at each of those heights.
Thanks, Jack.
All right, thank you very much. That wraps up our second lightning talk session. Is Jim presenter?
Yes.
I thought he wanted to run his own slides.
He asked us to run the slides for him. Why don't you follow?
Thank you, Lauren. Very excited about the field trip tomorrow. Jim, could you confirm if we're running your slides or you're running your own?
I assumed I was running mine, but it's fine if you run them, as long as I will try by words to point out some things. That's all.
Okay, no, why don't we try, if you're able to share, I think Brian set you up for that.
I just don't see the option to select that.
Oh, he's still clicking it. So it should appear. As Jim is getting set up, folks, we're moving into our last two presentations today. Jim is giving us a talk about, getting a weird echo. The geology site that we're going to tomorrow, so the geologic history of Bruneau Dunes. And then we are going to hear from Brian about the dune field trip logistics.
And I still don't see it. I'm okay if you guys run the slides.
Okay, yeah, we'll go ahead and run it. This one.
So I'll just be saying next.
That works. No. 1650. Yep.
That's it.
Perfect. Take it away, Jim.
I am sorry I won't be with you out in the field. I love being at the Bruneau Dunes. I've lost count of how many times I've been there for a variety of reasons. I think you will enjoy the day. I do hope you get a little bit of wind for some of those wonderful instruments that were just highlighted. What I want to do for you is give you a real quick introduction to the basic geology, and this is perhaps most useful for engineers who maybe haven't either been there or been exposed to an active aeolian setting. But when we're starting with geology, we're going to start with the bedrock, which is on that left picture, Columbia River basalts. B is Bruneau, and SRP is the next slide. Next, please. There we go. So Snake River Plain is a extensive volcanic complex that sort of is the bedrock in the area. It dates from roughly 14 million years at the lower left and present close to the upper right. And the plain is sort of that smooth area that makes a kind of V shape. The yellow dot is Bruneau. So all of the bedrock around the Bruneau area is volcanic material, and the little diagram from a Greeley paper really illustrates what it looks like. It's a series of very low shields, like the top picture, and the flows interlace and interact with each other. When I say low, I mean slow. The typical flank slopes are like 1 degree. So you only visually see it at a distance. You don't really recognize much of the structure when you're standing on it. So that's kind of the volcanic bedrock. Why does the age progress to the right? Because this is a hotspot trace, and Yellowstone, which is up at the upper right of the plains area, is still the active hotspot. Next, please. Now, superposed on those basalts are things that will be more relevant to the Bruneau history. This is a oblique picture I took out of a commercial jet when I was leaving Boise one morning. And you see the Snake River at the far right, but the dunes and the park, in fact, are within a sort of circular area. That is a cutoff meander loop from the former Snake River. And the dunes have formed in that. Well, the cutoff meander is formed in something called the Bruneau and the Glens Ferry Formation sediments. They are lower Pleistocene, that's roughly 1.5 million years. They are sediments, and that's critical to the rest of the story. Next, but what we're going to focus on are the dunes in the very center of it. Next, please. So here's a Google Earth view looking vertically down on the sand dunes. The lake is the sort of greenish color to the north of the main dune complex. And there is a slightly smaller dune just to the north of the lake. The parking area is not far from that. And I believe your demonstration area will be to the left of that slightly larger one. There is an even smaller dune, and it's somewhere in that vicinity that the demo will be set up tomorrow. The bottom pictures are topographic maps, one from 1948 and then one from 2013. And at this contour interval, they don't look different. That is not surprising at sort of the typical aerial photography scale. You can't resolve any changes, but things are indeed happening at the dunes. Next, please. Now, the only literature really on the dunes, and particularly the geology of the dunes, is this 1973 master's thesis by James Murphy. And the ranchers in the area called this place Eagle Cove. So his thesis title was about Eagle Cove, but he was in fact discussing the origin of the dunes in that area. And he included this plate in his thesis. These are the local names. That is what the local ranchers would refer to when they were in the area. And you'll notice Little Sahara, that's sand blowing to the south of the main dune complex, the North Dune Field blowing around the north end of the complex. And in fact, I believe your demo area will be close to where the head of the arrow of the North Dunefield name is. It's somewhere down in that vicinity. At the bottom, in the sort of dark hachured texture, that's the dune segment itself. It's two main large dune ridges that we'll talk about in a second, and then something that Murphy called the Bruneau Dune Crater. That again is local naming, but we're going to talk more about that as well. Next. So this is a picture of what it looks like next to the lake. Beautiful setting, whatever season you're there, I think you're going to enjoy it. A table in the Murphy thesis has the only published sort of compositional information I have for the dunes. And it is, you know, in percentage by volume, but it gives you a good idea that the bulk of the material is quartz. That's not surprising. Then feldspar, heavy minerals, which he said in his text is basically small basalt fragments, and then some magnetite. Now, this is interesting because it is a fairly good match to within about 5% of that Bruneau and Glens Ferry materials surrounding the dunes. And that is interesting because there was some question, was all of this sand deposited by the Bonneville floods that proceeded down the Snake River? We'll get to that in a second, but the answer is no, because those heavy mineral or basalt fragments are less than 10% of the sand volume, so that it was not eroded basalt that is making up the sand. It is eroded something else, and that something else are the sediments from the surrounding materials in which the cut-off meander loop carved itself into. Next slide. So there are isolated deposits of pluvial sediments on the floor of the basin in which the sand is located, but it looks like it is superposed on some sand as well. I would love for some Holocene geomorphologists or sedimentologists to look at this and publish about it. Absolutely beautiful ripple structures being eroded out when you get up close to it. And the speculation that Murphy made, and that's as far as I agree with it as far as I know from the information I can find, is that it just postdates the Bonneville deposition. I would just add the caveat that it may actually be in the late stages of that Bonneville deposition, as we'll talk about in just a second. Next. So where is that? That red square is where those pluvial deposits are. Now there are other outcrops of it scattered around, but this is one of the best ones highlighted in the Murphy thesis, and is easy to get to if you are just walking along the northern margin of the lake. You just keep the lake to your right, and you can't miss seeing a nice outcrop of the pluvial sediments. This is an oblique view of Google Earth, sort of looking along one of the two dune ridge crests towards the second, and that kind of oblong, funny structure, that's the crater. Next slide. This is a picture I took in 2012 looking west, and it does have a roughly bowl shape. Now it changes with strong wind patterns, but the locals called it a crater. That's not a bad description because it looks like a hole in the ground. Murphy did a good analysis and concluded that it is a merger of two offset dune ridge ends that just from the local wind fields twist around and make a circular-like depression. And it has nothing related to an impact type origin for the crater. Next slide. So here is a slightly different perspective. You can still see that crater-like feature, but the red line is where the trail goes if you want to get up onto the top of the main, the larger of the two dune ridges. P is the parking area, and it is a unmarked but reasonably well-trafficked trail through some low trees. In other words, you have to keep watching where you're stepping, but it's pretty easy to follow that beaten path through the small trees. And once you exit them, then you can just head up the slope to the ridge crest, which is exactly what we did for the field trip in the 4th Planetary Dunes workshop. Next slide. A slightly different perspective because now we're looking along the south end of the larger of the two sand ridges. The sort of broad sandy area right in the center of this view is a sand ramp. And that is a good word for it. It's actually fairly gentle should you want to walk up to the ridge crest that way, but you have to get through that same tangle of vegetation. Might as well just follow the trail and go up from there. If you have the time and the inclination, I strongly suggest that you get up to the ridge. It is a wonderful view of the dunes and just the setting. You will see that you are in a depression caused by the cutoff meander, and about 280 degrees or so of that depression is still present. And the opening is towards the Snake River. Next slide. Well, now we'll switch to the south end of the dunes, and this is where Steve Scheidt and I spent a few days doing differential GPS surveying along the south end. We had a very specific goal in mind. We made 10 different transects across the south end with the goal of having good topography that we could then compare to some of the DTM information that was beginning to get quite frequent from high-rise images of transverse aeolian ridges, TAR. So that was the goal of our paper. Well, there Steve is getting the surveying equipment set up in our base station, which we then tied to known non-movable features near the parking structures, the structures near the parking area. That's what I tried to say, to be able to geo-reference from year to year when we made some of the subsequent surveys. Next slide. Here are just 4 examples, and you'll notice that the vertical scale changes dramatically. B has 1 meter for the intervals in height, E is 2, H is 5, and J is 10. So the overall height of the edge of the dune is steadily increasing. And that was the reason we wanted to get this. That very symmetric profile shown in J is very typical of the tar features on Mars. It's just these are whoppers. These are bigger than just about any tar we have ever found on Mars. The reason for that will be apparent in just a minute. The colors in the little inset there refer to the colors of the lines, and that's just where the different profiles came from in our sequence of 10. Next slide. Well, here Steve is doing one of our last surveys, and you say, well, where is he? Next step. That little spot is 5'8" Steve Scheidt carrying the survey rod, and I was well further down the south on the dunes just to get a picture. I don't even have the top of the dune complex in the picture here. This is a massive amount of sand, and I'm very glad that Steve's a young postdoc was willing to do the surveying. I got really tired out quickly trudging up what is essentially a slip face on both sides of the ridge once you are at the top. Next. This is the survey that came out of that result, and the steeper west side, 110 meters of relief down to the pretty significant break and slope at the base. Not quite the same amount of height on the east, but it is definitely a reversing sand dune. Next slide. And that was demonstrated by getting wind data from the RAWS system, the Remote Automated Weather Station. There are over 2,100 of these scattered around the US. They are used by the Forest Service, but the data are online. It's wonderful. They collect the wind and temperature and a variety of other measurements, typically every 15 minutes. And it's at least a 20-year record for most sites now. This was from 2010 figures we used in our paper, but they are very consistent with what Murphy found from looking at over 30 years of information from the same location, not the same equipment, but the same location, which was Mountain Home Air Force Base, about 21 kilometers northwest of the dunes themselves. The January wind rose shows that the winds tend to come from the southeast. The July one is the exact opposite. They tend to come from the northwest. So it is a seasonal bimodal wind pattern. And the intervening winds have aspects of both of them. And it's this fairly evenly distributed bimodal wind that makes these very nice sharp crested dunes. So that's where you're going to be tomorrow. I realized I didn't say much more about the Bonneville flood. There was some question about the date of when the Bonneville flood came down. Murphy's thesis and extract of that is in the PDF that's available on the, I think it's a block diagram is what Serena called it. In that subset, it mentions an age of 30,000 years for the flood. Well, the flood waters actually came into Eagle Cove. Now, it did not have the high energy phase, which was concentrated more in the deeper parts of the channel. But that led some people to wonder, was the sand from the Bonneville flood? More recent cosmogenic exposure ages and things like that place the date of the flood at about 18,000 years. And the sedimentology says pretty distinctly that it is not primarily sand from the flood, but it is sand eroded from the surrounding mountains or surrounding sediments. That's it. If there's time, I'll take a few questions. And if not, just email me.
No, excellent. Thank you very much, Jim. We do have time for a few questions if folks have any. I'm not able to see the online. Can we pull up the chat? Thanks. Any questions in room?
I will add that you will be visiting or seeing some of the largest freestanding sand dunes in North America. There was a little bit of debate as to whether they were the tallest. And so Andrew Valdez, who was integral to the 7th Dune workshop, he brought a survey setup with him to Bruneau when I was there once, surveyed it, and he has parts of Great Sand Dunes that are slightly taller. It's just in the literature, Great Sand Dunes is banked up against a mountain range. And so it is not freestanding like the Bruneau Dunes.
Jim, Justin Crevier from Boise State. Thank you for that. That was fascinating. I had a question, having been out there a couple of times with my boys, actually, and there's that standing lake, but nothing, no real above ground source. Could you tell us where that small lake sort of gets fed from? Is there an aquifer beneath there, or is there some other kind of source for the water? Thank you.
Great question. And I should have included that in the talk. In fact, the reason you don't see the source is that it is groundwater, and you are seeing the exposure of the top of the water table in that area. So the lake volume actually goes up and down as the groundwater table is rising and lowering depending on what the seasonal rains are like. So that's the reason you don't see it. It is related to an aquifer. I don't know much about the aquifer itself. It's just that the lake level is the exposure of where that groundwater table top is.
Excellent. Thank you. I think we can move on to field trip logistics. Could we stop the record? There's no reason to record the field trip logistics. We can stop, keep live streaming. I guess it doesn't matter. Sure. Okay. Brian's doing that.
Oh, it's falling, Serena. Great. Okay, let's see. Is that good? I'm Mike now, right? You guys can hear me? Sure.
You're good.
That's why it's not working. Oh, great. There you go. I'm left-eared, not right-eared. That's the problem. Let's see. How do we get out of? Sorry, we put mine up here too, didn't we? Yeah, okay. Do I need it over here?
Are you trying to share this?
Yeah, that's what I want to show. Yeah. Although it's not like online people need to see it, but may as well, right? Yeah, that's right. That's right. Perfect. Thank you. And this will advance me. Should. Great. Okay. Yeah. Thanks. And again, welcome everyone to Boise. We're really excited to have you here. As you might imagine, we don't have conferences like this very often, and so it's really exciting for us to be able to host you all.
I know Dana, who's our host here at Osher, was really excited to have you all. And we may have some of the Osher members join us in the field tomorrow. So if you see folks you don't recognize, they may be some of the members who are letting us use their really nice space here. So I want to give you a quick rundown of what all's going to happen tomorrow logistically. Now you've heard a little bit about the science. Let me tell you what's going to happen logistically. You can go to this redirect URL to actually see a Google map of our site and a field guide that Jim helped us put together. Lots of other kind of cool stuff. So here's our schedule for tomorrow. About 8:30, we're going to gather here in the parking lot at the Yankee building to pile into cars and pick up box lunches. Oh, one point that I don't think has been made yet today. If you have a car and are willing to drive people, there's a driver sign up sheet in the Certbury. And I guess, yeah, Serena, if you bring it out, that'd be great. I think we have plenty of cars for everybody. So, but please, if you're willing to drive, let us know. You don't need 4-wheel drive. We're not going off road. I think the worst we have is a gravel road, but it's very well maintained. So shouldn't be a hassle for anybody. So 8:30 tomorrow morning, we're going to show up here. We have box lunches for you, sandwiches with chips and drinks or water. And Dana bought for us. Yeah, perfect. Here's the sign up sheet. Yeah, thank you. Dana bought for you cooler bags with the Osher logo on them that you can take with you. So have something to put your lunch in. So 8:30, start showing up here in the parking lot, get your lunch and your bag. We'll leave by about 9 and head out, and I'll show you the directions in a second. It's about an hour's drive, but I've given us an hour and a half to give just plenty of time in case people need to stop for bathrooms. And then we will meet Christy and her group out at the field site about 10:30, 11 o'clock. Does that sound about right, Christy? 11. We'll go slow. It will be a little windy tomorrow. Yeah. So Christy advises folks to put some kind of a mask on and maybe some bandana because there will be things suspended in the air. So worth keeping in mind. So we'll have a presentation. This is all very notional, so we can be very flexible, but sort of a presentation by Christy and her group of the really amazing instrument setup that she has out there. 12 is lunch, so you're welcome to have lunch then, whenever. And then we'll have presentations by Jack. Oh, is Muhammad here? He's not here. Okay, so I guess that didn't happen. All right, so nix that. And then, yeah, we'll basically just hang out, play with the instruments, talk science for a little bit. And then my goal is to try to get us out by about 4, so we can get back to Boise in time for dinner. Does that make sense? It's a very easy drive. I'll show you. So if folks feel like they don't want to all leave at the same time, they want to hang out, they want to climb the big dune, they go look at the lake, there's no need for us to all leave together. It's very hard to get lost on the way out there. So, for those of you who are worried about this, we got the nice box lunches. These are the nice sandwiches. There's a vegetarian option, turkey and roast beef. The vegetarian sandwich is dairy-free, vegan. The chips are vegan, vegetarian. There's gonna have a fruit cup that's vegan, and they got us a bottled water as well. So hopefully that will cover anyone who has other dietary restrictions. And then the other things are just roast beef and turkey. Oh, for sure. Yeah, I've got that in here. It's hopefully not going to be that hot tomorrow. The forecast is for 80s. It will be hot out on the sand though. So just be aware it's going to be hot. Bring water. I'm going to bring a little extra water, but don't plan on other people being able to provide you with water. Yeah, go ahead, Christy.
Oh, I guess you just said it. So we just need to bring water. It's been really hot the last 2 days out there, like to the point of like, I don't know. It's just really, really hot. And I think it's supposed to be about 90 tomorrow. So the temperature has increased a little bit.
Okay.
And the winds, unless the weather has changed, are supposed to be from around, I think 11 and 2, something like that. So hopefully we'll get some sand transport so we can see the sand tree too in action.
Yeah, so we're forecast for a little bit of wind, a couple miles an hour around the time we'll be there. Okay, so directions again. These are online. It's like I said, it's not hard to find. There's signs the whole way essentially. Get on 84 East, about an hour, 40 minutes. Kind of to Mountain Home. There's an exit here, exit 90, where you're going to get on to 51. Google Maps can get you there, so don't worry if you don't have the soft copy down. We're going to drive through Mountain Home, a small town. And then there's basically signs to Bruneau Sand Dune. And they have a really big flashing sign for the turnoff to the park. At least they did on Sunday. Is it still there? Okay. So hopefully it'll be easy to find the right turnoff. We unfortunately were not able to get the entrance fee waived. So it's $7 a car, not per person. So be sure to stop and pay that at the visitor center. Okay. If that's a hardship for anybody, let us know. We can probably take care of it. Yeah, go ahead, Jack. I think they take cards, you know? I think they take cards. It's not a problem because you can go to the visitor center and pay the fee there, and there's a register. So if there's not someone at the entrance, you can go to the visitor center, which is right next to the entrance. Okay. And I'll show you in a second, but we're gonna be down. There's a picnic area that we've rented out for our field site. Okay, so the entrance is kind of up here off the map. There'll be a road that we can take down. I think you can actually type in Bruneau Dunes Lake Picnic Area into Google and it'll take you right to this spot. So it should be pretty easy to find. But there's a map in the field guide. We're going to drive past. There's an observatory building and a steel reef, what's called the steel reef building. We're going to drive down here and then we're going to park along this road. This is a gravel road, but it's well maintained. So it shouldn't be rough or in bad shape. And then our field site is right about here. So basically we're going to park along here. There is a parking lot down here. It may be equidistant. I don't actually know. Do you know how much is it farther from the parking lot?
It's further from the parking lot. So
Yeah.
you should park on the road and you'll see a giant, strange metal thing. So
It won't be
hard to miss.
Doing giant metal thing. So it's easy to walk out there. The picnic area is covered, so there's a nice covered area, and then there's pit toilets down there. So for those who are not familiar, it's not like flush. It's a hole in the ground, but it has a big seat in a closed building, so you can have some privacy. Here's the field site. I took in a Google Photosphere, which you can find on the website again. It did not stitch together very well. I don't know why, but it was the sand was wet when we were out there in May, and even then it was still saltating. It was really active. I don't know that we're going to get that kind of activity tomorrow, but we'll hopefully see something. So the point is that this sand does move, even when it's wet. Let's see. Okay, so yes, as Christy said, bring water, hats, sunscreen. I think most all of you, if not all of you, have been out into the field before. There are snakes. Have you seen any? We saw one last time. For those of you who were in the Planetary Dunes trip back in 2015, I think, right, there was a snake. So there are snakes. There may be scorpions. So those kinds of things. So I wouldn't wear these shoes. I wouldn't wear shorts. I'd wear, closed-toed shoes and the pants. But that's basically it. Any questions about any of that?
I would add that there's not a whole lot of cell phone reception when you get down to the picnic area, but if you drive back up to the visitor center, you can get cell phone reception there. Yeah, just cover yourself. Cover yourself, water, and I have sunscreen if you don't have any.
Yeah, I'll try to bring a little extra, but again, yeah, don't assume that you're going to be able to have it provided.
And come with design ideas, because this is all about like designing it, and argue with me about 2 to 4 or 5 anemometers. Polite, it'll be fun.
Anything else? Oh, yes. We're going to have a couple of reporters who are joining us. There's someone from the Idaho Statesman. She is a AAAS science fellow, science reporting fellow who's been stationed here in Boise. She's reporting for the local newspaper. So she's been invited to join us out in the field. So you may get a mic in your face at some point. You're perfectly welcome to refuse to answer anything. Plead the fifth if you feel so inclined. So she'll be there. And then we're going to have a film crew from Boise State filming the field experiment. They may also want to interview you. Again, you're not under any obligation at all to talk to any of them. We will have, I think I have media releases. They will have media release for you if they videotape you. But we're going to try to put this together. The footage for folks who are virtual is going to be posted online as soon as possible. So we're collecting this in part to provide an opportunity for virtual folks to at least get a sense for what we were doing in the field tomorrow. Okay, great. And I'm going to write my cell phone number up here. I'm going to wait till we turn the video off, but I'll write my cell phone number up here in case you need to get in touch with me on the way out there. So, okay, should be a lot of fun. And that's it.
That concludes our first day. So everyone have a nice dinner and we'll see you at 8:30 in the morning. If you haven't signed up yet to drive and you're willing to, please do so. Thank you all.